All right, so let's start again. Again, we are going to solve some of the problem from chapter 3. Okay. All right, so the first problem we are going to solve is this one. Okay, so here it says that suppose the football in the last problem. So remember that in last class, in last lecture, we solved a problem. Okay, let me go to that problem. So here we solve a problem, and this was something like this. So this is the origin. The football was kicked from this position, from the origin. Okay, so this was the origin, and it was basically the general problem. Okay, now in the next problem. In the next problem, this is the continuation of the last problem, but here you see that the football is kicked now from some height. So this is the, about 1 meter height. Okay, so it's a little bit different. Okay, so in the last problem we use this point as our origin. Okay, here we are going to use this point as our origin. Okay, other than that, it's very similar to the last problem. Okay, so let's see whether we can solve this problem or not. Okay, all right, so this player kicked the ball from this position, and similar to the last problem, v0 was v0 is 20 meter per second, and the angle is again 37 degree. Okay, so this means v0x is 15.8 meter per second that we calculated in the last problem, and v0y is 12 meter per second. Okay, so if you forget, the rule is v0x equal to v0 cosine theta, and v0y is v0 sine theta. Okay, so these are the rule. Okay, so by plugging the value here, we get this. Okay, all right. Now, now what it asks us to calculate? It asks us to calculate how far did the football travel before hitting the ground. So we have to calculate this distance. Okay, so these are the given information, and also it says that this height is 1 meter. Okay, so this height is 1 meter. Okay, and here in this case we choose this as our origin. So the x0 equal to 0 over there, and y0 equal to 0 is over there. Okay, all right. Now if I want to calculate x, okay, the only equation I can use is this v0x t. Actually x0 plus v0 x t. Okay, now the problem is this is 0, that is good, v0 x t. So we know v0 x, that is this, but we do not know t, right? So what is t? So t we cannot calculate from the x component equations. We have another equation for x component, and that is vx equal to v0x, but this cannot be used, right? There is no information about t, so this cannot be used. Now we have to do we have to calculate t similar to one of the last problem by using the y component equation. Okay, so let's start with this equation, y equal to y0 plus v0 yt minus half gt square. So this is one of the equation, and we can use this equation because other equation is this vy equal to v0y minus gt. Okay, so another equation was this, but this equation we cannot use because in this equation we have two unknown, vy and t. Okay, so again we cannot use this equation. This equation we can use because we know y, we know y0, we know v0y. Only unknown in this equation is t. So we can use this equation easily, although it may not that easy. Okay. All right. So what is y? Y is this height. Okay. Y is this height. So it would be -1, right? Because this line is the 0 line. Okay, y equal to 0 line. So everything below y equal to 0 line, I mean every y below y equal to 0 line will be 0. Yeah, I mean will be negative, not 0, sorry. Will be negative. So although this is 1 meter, the correct number will be -1 because it is y0 equal to 0 line, below the y0 equal to 0 line, and y0 is 0, v0y is 12, and the gravitational acceleration is 9.80. So 9.80 divided by 2 t squared. So what we have here, -1 equal to 12t minus 4.90 t squared. So let me rewrite this, and it looks like it's a quadratic equation. Okay, so let me rewrite it as a quadratic equation. Okay, so if I write as a quadratic equation, it gives me something like this. Okay, now remember that in one of the chapter, I think in chapter 2, we solve a quadratic equation. Okay, similar quadratic equation. So we have to now use the similar. We have to. Okay, so we have to use a similar trick to solve this quadratic equation. And remember that. Okay, let me erase something here. And remember that quadratic equation is something like this: ax squared plus bx plus c equal to 0. So if we have any equation something like this, then x equal to 2a minus b plus minus b squared minus 4ac. Okay, now if you compare this equation and this equation, then you can write t is equal to 2 times 4.90 minus 12 plus minus 12 square minus 4.90 and then -1. Okay, so these are the two equations, two solutions for t, one for plus, one for minus. Okay, then then if you solve this, you get something like this: t equal to 2.53 second, and for the negative one you get negative 0.0823 second. Okay, so because time here cannot be negative, so this is a unphysical solution. So time to go from here to here is 2.53 second. Okay, then once we know that, okay, then we can use this time to solve x. So x will be v0x is 15.8 and t equal to 2.53. Okay, so it will be about 40 meter. Okay, so from here to here is 40 meter. Okay, all right. All right. So let's move on. Now the next problem. Okay, so next problem tells us that suppose one of the Napoleon's cannons had a muzzle speed of this 60 meters per second. So initial speed is given. At what angle should it have been aimed to strike a target 320 meters away? Okay, so there are many ways to solve this problem. So here let's use the horizontal level range equation. Okay, so we can use our regular equation also, but let's use the horizontal level range, which we already derived in class, right? I mean in theory class. So what was the equation for the horizontal level range? The equation was something like this: R, the horizontal level range, is equal to V0 square sine 2 theta over the gravitational acceleration. Okay, so here R is given 320 meter. Okay, so this is R, this is the initial speed V0. Okay, we have to calculate theta, and we know already that what is the gravitational acceleration. Okay, so let's plug these values and see what we get. Okay, so if you okay, so before that we have to solve it for sine theta. So let's solve it for sine 2 theta. So it will be R times the gravitational acceleration over V0 square. Okay, so if you plug these three values here, you should get 0.871. Okay, and then 2 theta is sine inverse 0.871, and that gives me 2 theta is equal to 60.6 degree. Okay, and that means theta is equal to 60.6 divided by 2, so 30.3 degree. Okay, now the angle is if Napoleon project this cannon at 30.3 degree, it will be striking the ground at, I mean striking the target 320 meter away. Okay, but here is another twist. Okay, so remember that for horizontal level range, for each horizontal level range we have two angles, right? Remember that we discussed in class that for 60 degree and 30 degree the horizontal level range was the same. Okay, 75 degree and then 15 degree, the horizontal level range are the same. Okay, so here we have also the two angles. Okay, not only 30.3 degree, we have to find another angle for which we can also have the same horizontal level range. Okay, so how to calculate the another angle? So this is easy to calculate. Okay, another angle, as we discussed already during class, will be 90 minus this degree, so it will be 57.3 degree, a 57.7 degree. Okay, sorry, 59.7 degree, right? 59.7 degree, right? So that is possible because there is a trigonometric identity, and trigonometric identity tells us that sine 2 theta is equal to sine 180 degree minus 2 theta. Okay, all right, so what it means? It means, uh, uh, I mean, theta is equal to, I mean, in this case, theta is equal to 90 degree minus theta. Okay. So, I mean, you don't need to remember all those things if you don't want. The thing you have to remember that if we have a projectile motion problem, we could have two horizontal, same horizontal range for two different angles, and the angles are connected by this equation. Okay. So once we calculate one angle, the another angle will be 90 degree minus theta. Okay. For each theta, 90 degree, for 90 degree minus theta angle, we also have the same horizontal level range. All right. So the next few problem is about the relative velocities. Okay. So let's see what we have here. Okay. So you see already this kind of thing in theory lecture, right? So relative velocity is useful. I mean, this concept is useful when we have two, so for example, here two separate velocities acting on something. Okay, so for example, here on the boat, we have two velocities affecting its motion. One is the river current, and another is the boat's engine's velocity. Okay, so here the first question, it says that a boat's speed in still water is 1.8 meter per second. Okay, if the boat is north directly across a river whose westward current has speed 1.2 meter per second, at what upstream angle must the boat head? Okay, so what this boat's aim is to go straight. Okay, so no matter what is the current, its aim is to go straight. Okay, to land here. Okay, but the problem is if the boat goes directly this way, okay, because of the river current, it will actually go here, somewhere here, right? Because the river current will affect its motion. Okay, the target, the aim is to go here. Okay, so if it wants to go here, okay, and if it goes directly straight, then it will actually land somewhere here because of the river current. Okay, so to avoid this, what it has to do, the boat needs to go in this direction. Okay, boat needs to go in this direction. Okay, so then river current will bring it somewhere here. Okay, so now we need to understand at what angle the boat needs to go in this direction. Okay, so it can easily be calculated because we know the river current, the magnitude of the river current. Okay, and we also know the boat's velocity. Okay, we know both. Okay, so it's easy to calculate. So we basically know this magnitude, the magnitude of this line. Okay, magnitude of this line and magnitude of this line. Okay, so because we know this magnitude, we basically calculate this angle. And as you know that if you form a triangle here, so you see that this is a triangle. Okay, now for this triangle, tan theta will be, the tan theta is opposite divided by adjacent. Okay, and then here we know that hypotenuse and opposite, right? So this is opposite and this is hypotenuse. Okay, so we cannot use tan theta. So what we can use is sine theta, right? Sine theta is opposite by hypotenuse. Okay, so opposite is what? Opposite is 1.20, that is this one, and hypotenuse is 1.85. Okay, so this gives us 0.649. Okay, so because sine theta equal to 649, we basically need to know what is the angle. So the angle will be theta equal to sine inverse 0.649, and that would be, I already calculated, and it is 40.5 degree. Okay, so theta equal to 40.5 degree. Here again, make sure when you do this calculation, make sure to change the calculator mode to degree mode. All right, let's do another similar problem. All right, so again, it's very similar but not exactly similar. This time the boat engine's velocity is directly northward, okay, to the north, and the river current is to the west, okay, north and west. So what is the velocity of the boat relative to the shore? Now we have basically two velocities that are affecting boat's velocity. So the resultant velocity will be, okay, so if I write down the resultant velocity will be boat's velocity with respect to water. So it means boat with respect to water, okay, plus the water velocity with respect to shore. So this is the water velocity with respect to shore. Okay, now you see that if we have this one and this one, okay, if we have two vector, it looks like we can form the tail to tip method, right? So the tail to tip method, if we use here, we can write that the resultant vector will be this one. Okay, so this is the first vector, this is the second vector, and it is already drawn very similar to what we want to form a tail to tip method. So the resultant vector will be from the tail of the first vector to the tip of the second vector. Okay, so it's very simple here, right? Now you see that here the magnitude of this vector you can calculate from Pythagorean theorem. That means the vector magnitude will be this plus this, right? Square root of the boat's velocity plus the current's velocity. Okay, and now if you plug them correctly, this is current velocity, this is boat's velocity. So if you plug them here correctly, you should get 2.21 meter per second. Okay, so this is the magnitude of the boat's velocity. The resultant velocity because of both boat engine's velocity and the water's velocity. Okay, now this is the magnitude. It asks us to calculate also the direction. So you see the magnitude and direction both. So how to calculate the direction? So direction mean this angle. Okay, so we can use tan theta or any theta because now we know all the three sides of this triangle. Okay, so we can use tan theta. Tan theta will be opposite VWS divided by adjacent. Adjacent will be BW. So that is 1.20 divided by 1.85, and again that is equal to 0.649. So theta will be tan inverse 0.649, and now this will be 33.0 degree. Okay, all right. All right, so the last problem for today's lecture is this one. Okay, and this is very similar to the last problem. I mean, problem number 9. Okay, and it says that the Cleveland is approximately 300 miles east of Chicago. Okay, so east means okay, so east means, so let's say Chicago is here. Okay, so east means in this side. Okay, so this is Cleveland. All right, a plane leaves Chicago flying due east. Okay, okay, so the plane is flying in this direction. Okay, at 500 mile per hour. Okay, so here it is mile per hour. So this is the plane's speed. Okay, VP. Okay, now the thing is, the pilot forget to check the weather and does not know that the wind is blowing to the south at 100 mile per hour. So you know that the wind is blowing in this direction. Okay, this is the south. So south. Okay, so that means wind is also affecting the plane's velocity, right? So this is plane's engine velocity. Now again, there is a velocity that is due to the wind, and that is 100 mile per hour. So this is okay, let me write V wind, and that is 100 mile per hour. Okay, so 100 mile per hour, and then here we also have 500 mile per hour. Okay, so the thing is, what is the resultant velocity? Okay, what is the net velocity for this plane? Okay, so similar to the last problem. Okay, it is exactly similar to the last problem. So we can draw a line. You see that this is the first vector, this is the second vector. Okay, so we can draw this line using the tail to tip method. Okay, and this is the resultant velocity. Okay, if I call it V, the resultant velocity, and the magnitude of this velocity will be just the Pythagorean. I mean, we can determine by using the Pythagorean theorem, right? So it is 500 square plus 100 square. So the resultant velocity will be 510 mile per hour. Okay. Now we also want to know what is this theta. So if I want to know this theta, tan theta will be opposite divided by adjacent. Okay, so this is 100, this is 500, so this is 0.20. So theta will be tan inverse 0.20. Okay, and then that is equal to 11.3 degree. So the plane is off by 11.3 degree. Okay, all right, so I'm going to stop here. Okay, in the next class we are going to start a new chapter, chapter 4, and there we are going to learn about dynamics. So we are going to start we are going to learn about force and Newton's laws of motion.